Okay, so we were dealing with rotations. If you remember, we were looking at certain examples of rotations. Now let's just try to make a few formal definitions that you will be, some terminology that you will see quite often. Let's start with SO3, SU2, and the Euler angles. Now, what we call a rotation is something that basically doesn't change the length of vectors. So if we have a vector, any vector, let's say R, it will, or let's say V, V1, V2, V3. So we have these three numbers. So V squared, which will be V1 squared plus V2 squared plus V3 squared. Well, a rotation is something that doesn't change this combination. Now, all the rotations that do not change this, all transformations, that leave invariant V1 squared plus V2 squared plus V3 squared. Let's call this V squared. Well, this is what we call ON. It's called orthogonal O3 in this case. Orthogonal group. Now we can look at these as some kind of matrices. Keep in mind that V1 squared plus V2 squared plus V3 squared. This we can also write as the row matrix, V1, V2, V3, multiplied with the column matrix, V1, V2, V3. Let's call this also V. So this is V transpose. So let's look at the transformation that leaves V squared in a transformation of V. Let's say V goes to some matrix multiplied by V. So V transpose V will just becomes V transpose R times V. So if this is to be invariant, what we need is R transpose R should be equal to the identity matrix. So we can also say that ON is all 3 by 3 matrices are such that R transpose R is equal to the identity matrix. Now this is not the group of rotations. This is a bit larger than the group of rotations. You see, if you look at, for example, R is equal to minus 1, 1, 1. Or this is usually called P, some form of P. If you look at this one, P transpose is actually P, and P transpose P is the identity element. So this tells me that P is a member of ON. But P is definitely not a rotation. It just changes the x-axis with the minus x-axis, or the x component to the minus x component. So it's not really a rotation. Now the interesting property of P, well, let's look at R transpose R. This is equal to 1. If you take the determinant of both sides, determinant of R transpose R, this is 1. But the determinant of the product of two matrices is the product of the determinants. The determinant of the transpose of a matrix is itself. And hence, the determinant of any element of this ON is either plus 1 or minus 1. And if you look at this, well, let me just call this M rather than P. It's called mirror symmetry. Now the determinant of M, what's the determinant of M? -1. It's a diagonal matrix. The determinant of a matrix is just the product of the diagonals, eigenvalues. So -1 times 1 times 1 is, determinant of M is just -1. Now we define another group, SO3, let's say. In general it can be, and since we are working with 3 dimensions, we only have the 3. SON is defined just similar to ON. It's made of 3 by 3 matrices. R transpose R is equal to 1, but we have one additional condition, that the determinant of R should be 1. So M, which is not a rotation, is not a member of SO3. This is called a special orthogonal group. Of 3 by 3 matrices. Now this is the group of rotations. Any rotation is a member of this group, SO3. Now we had already also seen one more thing when we were looking at the 2-component formalism for spinors, for rotations. If you remember, we had defined this object sigma dot A, which was AZ, or sigma dot N, no, sigma dot A, AZ minus AZ, AX minus I, AY, AX plus I, AY. Then U dagger sigma dot A U was just sigma dot the rotated A, where U was our rotation matrix. Minus I sigma dot N, we are talking about rotations around this N direction by an angle theta. So these 2 by 2 matrices, they also form some kind of a representation of the rotation matrix. So we can show the rotation operation either by SO3 or in this case U2. Now let us define UN in general. Well, UN is very similar to ON here, but in the case of the unitary group, we are not talking about the real numbers, we are talking about complex numbers. So basically, we have C1 absolute squared plus C2 absolute squared plus Cn absolute squared. So UN is defined as any transformation that leaves that sum invariant. Again, this thing we can just, in our case, this is basically the state matrix. And this product just corresponds to the norm of our state matrix in the 2 by 2 formalism. So the rotations should leave the norm of my state matrix invariant. Now this thing I can write as C dagger C, where I can define the C to be C1, C2, Cn. Now in the spin 1/2 case, n is just 2. So if you take any element of this SUN, UN, then C would just go to U times C. C dagger C will go to C dagger U times C. And we want this to be equal to C dagger C. But that tells me that U dagger U should be equal to 1. And if you look at the determinant, this also tells me that the determinant of U, the absolute value should be 1, or the determinant of U should be just e to power I alpha for some real number alpha. So here is our definition. Un is all the elements of U such that U dagger U is equal to 1. And Sun is all U such that U dagger U is equal to 1. Furthermore, determinant of U is equal to 1. In general, the determinant of U in Un can take any complex number with a unit norm. If you look at the O3, the possibilities were only plus or minus 1. And we had also seen that in this example, we can describe rotation by some matrix U. If you have any rotation, then there exists two unitary transformations that corresponds to the given rotation. So in that sense, SU2, let's say this is O3 plus O3. Okay, this is a bad notation. Don't show this notation to a mathematician. But it's just like SU2 is just twice SO3. Because for every rotation, you have basically two rotations, two unitary matrices U. Now, if you look at an arbitrary 2x2 unitary matrix, let's do some exercise. Let's say U is a member of SU2. In general, we can write U as A, B, C, and D. Of course, for arbitrary A, B, C, and D, this is not a unitary matrix. So what we want is U dagger U. This should be the identity matrix. So this tells me that A star, B star, C star, D star multiplied by A, B, C, and D, this should be 1. Or if you do that matrix multiplication, you will get A absolute squared plus C absolute squared. This is the 1, 1 element. The 1, 2 element is A star B plus C star D. And 2, 1 element is B star A plus D star C. And the 2, 2 element is B star B squared plus D squared. This should be equal to 1, 1, 0, 0. So we had these four complex numbers. Now we have four complex equations that these four complex numbers should satisfy. A squared plus C squared should be 1. B squared plus D squared should be 1. A star B plus C star D should be equal to 0. And this equation over here, B star A plus D star C should also be equal to 0, but this equation is the same as the previous one, just the complex conjugate. Now, how can we solve these equations? You see, if you look at these equations, well, let's start with the last one. The last one tells me that A star B should be equal to C minus C star D. So how can we solve these equations? And well, you see, if you look at let's look at these two equations. The first guess would be either the absolute value of A is equal to the absolute value of B, and the absolute value of C is equal to the absolute value of D. Then those two equations are automatically satisfied. And if that is satisfied, well, this equation also tells me that the absolute value of A times absolute value of B should be equal to the absolute value of C, absolute value of D. So these three equations is satisfied if A is equal to, well, D, and C is equal to B. This is satisfied, and this is satisfied. If this condition holds. Now let's look at this one. Well, that, you see, the norm of A is equal to the norm of D, but A cannot be equal to D. But the choice is A should be equal to D star, and B is equal to C star, with some signs somewhere. Now let's put that minus sign over here. This is the solution. So my U just becomes, of course I have this additional constraint that A squared plus B squared is equal to 1. This is an additional constraint. So you see my U is A, B, well this is minus B star, D is A star. With the determinant of U, this is equal to A squared plus B squared, this should be equal to 1. So check, this is an element of our SU2. Now you see we had already derived, for example, the rotations, the 2x2 representation of my rotations. U was equal to e exponential of minus I sigma dot, let's say, n, and had theta over 2. This matrix was equal to cosine theta over 2 minus I sigma dot n had sine theta over 2, which was e to the power minus I theta over 2, e to the power I theta over 2. Now let me just put in the correct expression. If you just put in the matrices, this is what you would obtain. Cosine theta over 2 minus I and z sine theta over 2 minus I nx minus ny sine theta over 2 minus I nx plus ny sine theta over 2 and cosine theta over 2 plus I and z sine theta over 2. And well, you see this is of this form. Yeah, I mean, we had already said that any unitary 2x2 matrix should have this form. And we have seen that this matrix, which we had studied last week, does have that form. You can just identify relate the angles with A and B. You see that the real part of A is cosine theta over 2. Imaginary part of A is minus nz sine theta over 2. Real part of B is minus ny sine theta over 2. And imaginary part of B is minus nx sine theta over 2. So we know what the coefficients A and B are. Now let's look at Euler. Any questions up to this point? So this just tells me that any rotation I can write it either as a 2x2 matrix, as a member of SU2, or as a 3x3 matrix, a member of O3, SO3. Now the Euler angles will be a bit confusing, let's say. Now, for rotations, we have already been writing down rotations, and we have been saying that rotations can be written as minus I sigma dot n hat theta over 2, for a 2 by 2 matrix at least. Or in general, exponential of minus I over h bar j dot n hat theta. This is for an arbitrary system, j being the generators of rotations. Now, to specify this notation, we need to know what n hat is. And this n hat, we are rotating around n hat. To specify this n hat, we can say either, well, you see, if you choose your coordinate axis, if this is our n hat, it's enough to know this angle theta and this angle phi. So that is 2 parameters. Well, let me just change this rotation angle by alpha. So to specify the axis of rotation, I need 2 parameters. Furthermore, to specify the angle of rotation, 1 parameter. So in total, to specify an arbitrary rotation, we need 3 parameters. This is if you tell me these 3 parameters, I can uniquely specify an arbitrary rotation. This is one way of parameterizing those rotations, specifying the theta and phi angle of the unit rotation axis, and then specify how much we rotate around that axis. Well, this is not, conventionally this is not much used, so rather than specifying a rotation by these 3 parameters, most of the time what we do is, you see, if you start with, let's say, any coordinate axis, x, y, and z. After rotating, these angles become, okay, so let me try to draw it like this. Let's say this is z prime, this is y prime, this is x prime. So you start with some coordinate axis, x, y, z. After rotation, that axis just has a new orientation after an arbitrary rotation. You start from here, then you reach here. Now, most of the time what we do is we just look at a disk. What happens to the a disk on the xy plane after this rotation? So initially this was our disk. That is the initial disk. Let me use a different color. This is the z prime axis, this is the y prime axis, this is the x prime axis. And that disk, that unit disk on the xy plane, let's say after rotations it becomes this one. This is my new disk. Yes, I started with this disk. Well, it's hard to visualize this thing. Come here. And can somebody give me a pen or pencil? And come here so that you will be able to see. Let's see. This is my x-axis. This is my y-axis. Similarly on the plane. Now, after a rotation, okay, this is the z-axis. After a rotation, it will take this form. So there is this. Now there is this new disk. This plane kind of becomes this plane now. Also rotated like this. Now I have this plane. I also have this plane. Now this initial disk just becomes this disk. Now first of all, there is the angle between the z-axis here. Well, let me put this is my z-axis, this was my new z-axis, so I can specify this angle between the z-axis. That angle is what we call, it should be alpha, beta. Now the second thing I will be using is, you see there is this line, the intersection between these two disks. That intersection line, let me see, makes an angle alpha with the initial y-axis. You see, they intersect along this line, these two disks. So there is an angle alpha. And then on this disk, this intersection line makes an angle alpha with the initial y-axis, and it makes an angle gamma, right, with the final y-axis. Okay. So I can think about these rotations. You see, one parameter, one thing I have to fix is I have to make an angle with the new z-axis makes an angle beta with the original z-axis. So I have to, if I want to specify this rotation, I have to tilt my axis around the z-axis. I have to tilt my z-axis first. Well, I can do it, you can do it whichever way you like. Let's see, the convention that we will, okay, so you can do it whichever way you like. You can just rotate your system around any axis passing through the xy plane. Now, the first thing we do is usually just rotate the y-axis. Okay, let me do it step by step now. So this is the initial coordinate axis. X, Y, and Z. And my unrotated axes, let me put X prime, Y prime, Z prime. Now, first I rotate around the y-axis. You see, what I'm going to do is first align my y prime axis with that line which is the intersection of these two disks, the unrotated disk and the rotated disk. So that's the first thing I will do. So first a rotation around the z-axis. By alpha. So that is because the angle that the intersection line makes with the initial y-axis. So after rotation, you see this is my initial coordinates. Z prime is still in the direction of Z. My X prime now makes an angle alpha with X, and my Y prime makes an angle alpha with Y. I just rotated around the Z, so my XY axis just became X prime, these new two axes. This is my new Y prime axis. Now, this is the direction, let's say this is X, this is Y, this is Z. I started from here, I rotated by alpha. I want to keep this to be the intersection line of the disk, the rotated disk, and the new disk. This will be my intersection line. The first thing I do is I rotate around this axis so that the disk is now tilted relative to the original XY planes. It will be now tilted. So, but since I'm rotating around this axis stays both in the initial disk and also in the rotated disk. So that line is fixed. So the second transformation is rotate around Y prime axis by, well, the rotation angle beta. You see, if I tilt around beta, Z is no longer invariant. Z should be tilted by beta. So that is why I'm tilting it by beta. So these are X, Y, and Z. Since I'm rotating around Y prime, this is still my Y prime. But now my Z is tilted. So is X prime. Now, still Y prime axis is on the XY plane. You see, if you look at this graph, Y prime axis is not in the XY plane. So what I need to do is, first of all, I need to keep the intersection point fixed. I mean, now the disk is already tilted to its final orientation. Z-axis is in its final orientation now. The disk is in its final orientation. I have to keep the disk fixed. But still, I have to rotate the Y prime axis. The way to do it is just I rotate around the Z prime axis. And so rotate around Z prime axis. If I rotate around the Z prime axis, Y prime will no longer stay in the XY plane. It will start, it should eventually make an angle gamma with the initial Y prime axis. So I rotate around the Z prime axis by gamma. The final one. You see, after these two, okay, this is the final rotated system. And X prime, Y prime, Z prime are all in different planes. None of them stay in the XY plane. X prime is not in the XY plane. You see, maybe it will be easier to visualize it if I stand up. This is the X, this is the Y, this is the Z. This is the unrotated system. After I rotate, my new system is this one. None of them are in the XY plane, not necessarily. So how do I rotate it? First, okay, this is my XY plane. The first thing I do is I rotate by alpha. So this is the line through which the unrotated disk and the rotated disk intersect. This is my first rotation. My second rotation is around this line because I want to leave that invariant. So I rotate my disk. Now this is my final orientation, but still Y prime is in the XY plane. Now I need to rotate it further so that Y prime makes this angle with the initial Y axis, with this axis, with the XY plane, but I also need to keep this intersection line invariant. The way to do it, I just rotate it like this. So this is my final orientation of my axis. So this rotation doesn't change the new Z-axis. It doesn't change this intersection line, but it rotates the X prime and Y prime. And then I obtain the final orientation. So I'm rotating around the Z prime. So Z prime stays where it is, but X prime and Y prime, they are now lifted from the XY plane. So this is X prime, this is Y prime. That is still the line along which the original XY plane and the rotated XY plane, they intersect. And here, this is what we call gamma. This is what we called beta. And this is what we call alpha. Again, keep in mind, I started from this one. The rotated system should be this one. I started like this. The rotated system should look like this. Now this is my XY plane, the new XY plane. This is the initial XY plane. And these two planes intersect along that line. So that is first I rotate to that line. My y-axis now coincides with that line. Now I rotate my z-axis. Now this xy, the rotated xy axis is exactly the same as what I was looking for after the second step. But the rotated x prime axis and the rotated y prime axis, they do not really overlap, because the rotated x prime axis and y prime axis are these ones, not this one. So that is why I make one more rotation, keeping the rotated xy plane fixed. So to get from here to there, first I need to rotate my xy plane from this one to this one. But this xy plane and this xy plane, they are the same thing. They're just rotated around the z-axis. So the first thing I achieve after two rotations is to obtain the rotated xy plane. And the final rotation just gives me how I should orient the new xy axis in this rotated xy plane. That fixes my rotation. These are called the Euler angles. But now I know how to rotate my system. Let's say these are alpha, beta, gamma. What did I do? I first rotated around the z by alpha. Then around the y prime axis by beta. Then around the z prime axis by gamma. Well, let me Now you see, what we are trying to achieve is eventually, in various processes, what we will be needing is the amplitudes that a given system with a given spin oriented in one direction will be found with a given spin in a different direction. So this matrix, you see, the spin orientation of the final object can be specified by these three numbers, alpha, beta, and gamma. So if I start with some spin oriented in the z-axis, let's say, if I want to obtain an object with a spin in the z prime axis, I just multiply it with this one. So I will be rotating my spin cap. Of course, up to this point, everything is quite general. I mean, even if you have some arbitrary spin or angular momentum, it will be exactly this operation. Now, of course, there is something that's not so nice over here. You see, if you look at these rotations, these are not rotations around the x, y, z axis. They are rotations around the z prime and y prime. So what we would like to do is rather write them in terms of rotations around the x, y, z axes themselves. So that is the last thing we should do, and then it will be over. Now let's look at this y prime axis. Well, this y prime is this y prime that we are talking about. Now, if you want to rotate around the y prime axis an object, if you want to rotate an object around the y prime axis, well, the easiest thing will be first rotate your coordinate axis such that y coincides with y prime. Rotate around your new y-axis and rotate your coordinate axis back so that y-axis is back in its original position. You see, we know how to rotate around the x, y, and z axis. We know how to rotate an object around the x, y, or z axis. Those are what we call the active transformations. We also said that, okay, we can also talk about passive transformations where we rotate the coordinate axis. Now we want to rotate an object around the y prime axis. So let me first make a passive rotation around the z axis by alpha. That passive rotation will just make my y axis my new y prime axis. Right? You see, I will treat that first operation as a passive operation. I'm not rotating my system, but I'm rotating my coordinate axis. Well, passive rotations are the opposites of active rotations. So if you rotate your system, let's say, around the z-axis by, if you rotate it around the z-axis by, let's say, theta, it is the same thing as rotating your coordinate axis around the z-axis by minus theta. So that's why I have the inverse over there. But after this passive rotation, now y prime axis is my y axis. So I can rotate my system around the y axis by beta. But of course now I have to rotate back my coordinate axis to the initial orientation. Not inverse this time. So we have such an identity. Well, let me just use some shorthand notation. So what do we have? The rotation by these earlier angles, alpha, beta, and gamma. This is the same thing as rotation around the z prime axis by gamma. Rotation around the y prime axis by beta. And the rotation around the z axis by alpha. This is a rotation around the z prime axis by gamma. Now, rotation around the y prime axis, we just said that this is the rotation around the z axis by alpha, rotation around the y axis by beta, rotation around the z axis by inverse by alpha, dz alpha. So this is my dy prime beta. So you see these cancel. Nice. This is equal to dz prime gamma dz alpha dy beta. One gamma. So we still have the rotation around the z prime axis by gamma. So how can we do that? Now let me cheat a bit. Well, let's see. I will do a similar thing. You see, we obtain this beta by rotations around the y prime axis. So rotation around the z prime axis by gamma will be a rotation around the y prime axis by minus beta or inverse beta, then a rotation around the z axis by gamma, then a rotation around the y prime axis by beta. I basically do the same thing. So you see here, this is how we obtain the angle beta by rotating around the y prime axis. Now, to consider a rotation around the z prime axis, what I do is I first consider a passive transformation around the y prime axis, so that I'm actually rotating my coordinate system so that z aligns with z prime. Then I consider a rotation around my new z axis, which is nothing but my z prime axis, and then I rotate my axis back. This transformation just aligns my z-axis with the z-prime axis. That's the passive transformation. I treat it as a passive transformation. This is an active transformation which rotates around this new z-axis, and this rotates back my coordinate axis back to its initial coordinates. Well, we already know what dy prime is. You see, dy prime is dz alpha dz gamma, no, hold on, dy beta, dz alpha inverse, right? Now, hold on. Okay, so this is our new transformation. Now let's go back to the initial thing, d alpha beta gamma. This is dy prime beta, dz gamma, dy prime inverse beta, dy prime beta, dz alpha. Now this is 1. And dy prime beta is this one over here, dz alpha, dy beta, dz inverse alpha, dz gamma, dz alpha. If I didn't make some stupid mistake somewhere. So let me see. Yes. Now look at this one. They are all rotations around the z-axis. So that's nothing but a rotation around the z-axis by minus alpha plus gamma plus alpha. dz alpha, dy beta, dz gamma. So just take any spin state, act on it with this one, you obtain a spin state which is aligned in the alpha beta gamma direction. So if you want to calculate, for example, any matrix element, let's say J is equal to 1 over 2 m, J is equal to 1 over 2 m prime, but of course this is in an arbitrary direction. This is nothing but J is equal to 1/2 m prime d alpha beta gamma. J is equal to 1/2 m. which is usually denoted by the m prime for spin 1/2 systems alpha, beta, gamma. It just, these rotation matrices just give us these matrix elements. That if you have a spin system in one, spin aligned, let's say, in one direction, what is the amplitude that it will be aligned in some other direction? Well, these numbers are just tabulated, so if you want to use them, you don't need to derive them. You can just go look at the tables and just extract the numbers. Now, of course, we already know what these matrices are for spin 1/2 system. There are rotations around the z and the y axis. You can just put them up and find the explicit values if you like. I will not do it. Now, any questions up to this point? Well, these earlier angles can get a bit confusing. I strongly suggest you that you, when you go home, just try to come up with those rotations on your own. Well, you see, this looks simple, that expression. You can try to work it out for some other specifications of the rotations.
Where does the n come from?
Which n? Well, you see, so this is if you act on this with n, s dot n, what you get is h bar over 2 times m prime this is where the n comes from. And so it's an eigenket of the s dot n operator. The other one, j is equal to 1/2 m. If you act on this with sz, you get h bar over 2 times m. J is equal to 1 over 2m. Okay, let's give a 10-minute break, and now we will continue.